2E4 Lab Practical B Buckling of a strut. In this laboratory session, we will investigate the buckling of a number of struts with varying end conditions. Buckling is a form of sudden, large deformation experienced by a structure under compressive load. It occurs normal to the direction of application of the load. Ideally speaking, a perfectly straight strut subjected to a purely axial compressive load would compress and not buckle. Buckling is therefore a result of imperfections in the straightness of the strut and/or eccentricity in the applied loading. Buckling is a form of instability. It occurs suddenly with large changes in deformation but little change in loading. For this reason, it is a dangerous phenomenon and must be avoided in structural design. Whether a structure will buckle or crush depends upon the slenderness ratio of the element. This is defined as the ratio of the effective length to the least radius of gyration. Since the radius of gyration depends upon the cross-section of the element, the slenderness ratio can be described as the relationship between effective length and minimum cross-section dimension. Members with a high slenderness ratio will buckle, whilst those with a low slenderness ratio will crush. The effective length of a strut is the distance between successive inflection points of the buckle shape. It is defined as follows. C is the end condition factor and depends upon the support conditions. Possible values are as illustrated here. The minimum load that will cause buckling, known as the critical buckling load, depends upon the geometrical and mechanical properties of the strut. It is defined as follows. The Euler buckling curve shows the relationship between the slenderness ratio and critical buckling load. For a column pinned at both ends, it is as shown. This lab is split into two parts using two different pieces of equipment. Firstly, we will use the small buckling rig to observe the effects of the support conditions on the buckling ship. This small rig has four different support structures. Number 1. Fixed at each end. Number 2. Pinned at each end. Number 3. Pinned at one end, fixed at the other end. And number 4. Roller at one end, fixed at the other end. Force has been applied sequentially to each strut by pressing down on the top plate. Note the differing shapes of the buckling curve for the differing support conditions. Please use the scale to estimate the effective length for each case. For the second part of this lab, we will use the large rig to observe Euler buckling and demonstrate the effects of length and slenderness on how a strut buckles. The large buckling rig comprises a reaction frame and hydraulic jack which can be used to apply a force to the strut. Force is applied by way of a hand-operated wheel. The applied force can be measured in newtons via the dial gauge. We will test two different struts with different overall lengths. Their dimensions are as follows. This rig uses fixed supports at both ends. The struts are placed between the supports and locked into place. Force is then applied to the specimen via the hydraulic jack. Upon reaching the critical buckling load, the steel members are observed to buckle or deflect from the centre line. Please note the value observed for both specimens. You will need these force values for your calculations. Please also calculate the slenderness ratio and the radius of gyration from the given dimensions. This report is split into two parts, corresponding to the two experiments that were undertaken. Part A, effective end conditions. Draw the first mode shape for the 4 different end conditions encountered. Estimate the effective length using the scale next to the strut. Calculate the theoretical effective length for each bar in the small loading frame based on end conditions and original length, and compare it to the measured values. Comment on the results. Part B, effect of length. Measure the critical buckling load from the dial gauges for each of the 2 struts. Calculate the critical buckling loads for the bars with different length in the big loading frame and compare with the measured values. Plot the Euler buckling curve for the 2 struts. Use the cross-sectional dimensions to calculate A and assume that E is equal to 200 gigapascals. Plot the data from the measurements of the 2 struts, each as a single point, on the Euler buckling curve. Where do the 2 struts sit on this plot? How would you describe the 2 struts? How do you think they would fail? Your course lecturer will inform you soon as to the submission dates and methods. Best of luck with your report.